Hey, it's Mr. K doing a video for AP Physics 1, a little bit of AP Physics C in here too. Let's get started. We have rotational motion, and to start off we're just going to talk about what it is to move, and as we have seen before, to move a certain change in position, it's going to take us a certain change in time to do it, which means that's going to be some kind of velocity there. And another definition is, hey, if we change velocity, it's also going to take a certain amount of time to do it, and that's what we call acceleration. So everything that we do for kinematics is basically based off of this, and let's just turn it into some rotational motion. So we have this some kind of turntable. We're looking down on it, and we're going to put somebody over here. Let's call this guy Fred. So there's Fred, and then we're going to have Bob, because why not? So we got Fred and Bob, and Fred and Bob are going to be moving on this turntable, and they're going around in a circle. So they're going like this. So for one full rotation, Bob goes this outer distance, Fred goes this inner distance, and what you should know about circles is, hey, the bigger circle that you have, Peeves, what'd you do? What'd you do? You're okay. All right. Peeves is messing with the big ice block that I froze for her. But Bob goes around in the big circle, Fred goes around in a smaller circle. And while they go through the same amount of radians, the angles, the distance that Bob travels is much larger than the distance that Fred travels here. And so to look at that, if you wanted to consider, hey, what speed is Bob moving at? What speed is Fred moving at? Well, you would say, all right, how far did they go and how long did it take? And so for Bob, how far he went would be, let's say he's at some radius big R, whereas Fred would be at some radius big R divided by 2. So Bob, you went one full time around, you went 2 pi, you went an R for radius, and that is going to be divided by the time. That's going to give us the velocity of Bob. For Fred, he went some kind of 2 pi as well, but his radius is going to be R divided by 2, and that's going to take some time as well. So while the time is the same, what we get here is that Bob's velocity is 2 pi r over t. Fred's velocity is going to be pi r over t, which means that his velocity is going to be half the velocity of Bob. All right, and that's just because he's closer and he's actually half the radius in. So they're going around in the circle. And yeah, if you are moving around in a circle, don't forget that you do have centripetal force required to move you in that circle to keep you turning. But right now we're just talking about their motion as far as kinematics goes. And so, well, I guess kinematics would have acceleration as well. But let's move on with just the straight up motion of it. So Bob moves, Fred moves, they're moving at velocities. Bob has a velocity v, Fred has a velocity v over 2. Now if you wanted to consider the amount of angles that they go, well, Bob goes through an angle of 2 pi in a certain amount of time taken. Fred also goes in a certain amount of angles, 2 pi, in a certain amount of time taken. So these two things are the same, and we call this the angular velocity omega. So they would have the same angular velocity. Okay? So looking at the relationship here, if we wanted to talk about Bob or Fred, then we'd have to talk about their actual tangential velocity or their angular velocity. All right, and there is a relationship between the two, and the relationship is that Fred and Bob both travel in the same theta, but they have different r values. So theta times r would give you some actual distance value or an arc length. All right, if they go all the way around, this is just 2 pi r, and that arc length would go back and be divided by time to give you this velocity. So the relationship here, again, is that theta times r is the arc length, or usually we call that like delta x, an actual position change in meters. And if I went back to velocity, this theta times r is right here. Okay, so that theta times r divided by t, that is going to be the velocity. All right, and so we can say, oh, wait a minute. If we wanted to find omega, omega is just theta divided by time. That's omega, right? And these are very, very similar. Well, what's that last relationship there? If theta over r, or theta over t is going to be omega, theta over t times r is going to be v. Well, v is equal to omega, because that's this stuff, times r. All right, and that's going to go one step further, and we're going to say that the acceleration of them is going to be equal to the angular acceleration multiplied by r as well. All right. So what it comes down to here is that the acceleration that you know, as far as going in a straight line, this meters per second value, that is a change in velocity over a change in time. Okay. The angular acceleration is the change in angular velocity over the change in time. Very, very similar. The velocity that you know is a change in position over a change in time. The angular velocity is equal to a change in angles over a change in time. And then lastly, the position that you go through is just your final position minus your initial position. That's your change in position. And your change in theta, well, that's just your final theta minus your initial theta. So really it's just looking at your changes in angles. So what this says is, you know, we've got these equations of motion, these final velocities equal to initial velocity plus acceleration times time. Well, it should hold true that if we go at a certain with acceleration to change our speed, that it should hold true over here as well. So final angular acceleration is equal to initial angular velocity plus angular acceleration times the change in time. Okay, there's a second equation, final velocity squared equals initial velocity squared plus 2 times a times delta x, or how far you go. That's true over here too. Angular stuff is set up the exact same way. So really, no reason to really be worried about it. It's alpha now, and that's theta. And the way that we get from one to the other is we just divide all these things by the radius that you're at if you're moving in a circle. Or here we'd multiply by the radius to get to the tangential stuff. Last equation, change of position, initial velocity times time plus 1/2 a delta t squared. Here, change in position, theta, is equal to initial velocity times time plus 1/2 alpha t squared. So they're the exact same equations. If you're sitting there saying, well, this is stupid, I don't understand this, you are just, you're just giving yourself a mental block. It's the exact same stuff that we've been using the entire time, except now the units are different. Okay, so don't be like, rotation is really, really hard. It's the exact same stuff. Now, to talk about rotation, we do need to talk about one more thing, and that's going to be the right-hand rule. And this is just going to be a way to draw vectors for things that are rotating, because it's kind of hard to draw a vector. Let's say these guys are rotating in a circle, and what you might want to do is you might want to say, all right, well, here's Fred, and here's Bob. All right, and Bob is obviously moving faster than Fred. And if you want to show a lot of motion, then you would draw that. You would not draw that. Okay, so the right-hand rule is going to help you out. And we're going to continue in another video with rotational motion for angular velocity, or angular momentum and angular rotational kinetic energy. Losing my words here. But let's say that we have this disk and it is definitely rotating in that direction. Okay, the way that you would draw the vector for that is you would take your right hand. So here's my right hand, and I would make my right hand into a fist and have my thumb sticking out. And so wherever I rotated my fist, the thumb is always perpendicular to where I'm curling my fingers. Okay? And so if this disk is rotating like this about the y-axis, then I would curl my fingers in the direction of that, and my thumb would be sticking straight up. So for this disk rotating about the y-axis, I would say, all right, there is my angular velocity vector, omega. Okay? So to rotate and talk about the right-hand rule, I'm going to rotate and curl my fingers in the direction of rotation, which is going to be this way. And I'm just going to grab onto the axis of rotation. My thumb's going to stick up in the direction of the vector. If the disk was rotating the other way, I would curl my fingers the other way, and my thumb would be pointing down. And so this vector would actually be pointing down. So you can use that to draw out vectors for rotation. And so as another example, if I have this bar, let's say, and this bar is kind of pinned into the wall, well, gravity would act in the middle of the bar. Well, it would act all over, but on average, it would act in the middle. So there's your mg. So if this were to play out, this bar should rotate downwards. And as this bar rotated downwards, it would get an angular acceleration because there's a force acting to rotate it. Really what you got to look at is the sum of all torque on it, and torque is that force at some perpendicular distance away from a center of rotation. And so here we have this distance, call it r, and this force is mg, so we would have a torque of force gravity at radius r from the center of rotation. Now, if the force gravity was not perpendicular, we'd find the piece that was. And so an unbalanced torque is going to give some kind of acceleration, angular acceleration, based on what we call inertia. So I'll make another video for, again, the angular acceleration stuff with inertia. But right now, let's just talk a little bit about it. So to talk about this thing's going to rotate downwards. This is the axis of rotation, and so I'm going to rotate and clamp on. Wait, that's the wrong direction. It's going to be like this. So I'm going to rotate my fingers, and my thumb is going to go into my page here. And so again, here's my axis of rotation. It's coming out of the board just like this with my pen. And so I'm going to grab onto that in the rotation direction that's going to go, and my thumb would go into the page. And so as far as my angular acceleration is concerned, or as far as my torque is concerned as well, because that's what's causing the angular acceleration, my vector for that would go into the page. And the way that we draw that is a circle with an X. So imagine an arrow. In class, I would have shot you with an arrow or pointed an arrow at you and said, all right, if this arrow is coming straight at you, it would look like this. And so this would be out of the page. If the arrow was going away from you, like you shot it, it would be going into the page where you see the X with the fletching, the feathers in the back. Okay, so there's ways to draw vectors in 3 dimensions because you need to use the right-hand rule to understand what's going on with the acceleration and the torque and the angular velocity of all these things. So again, if we have this thing rotating like this, let's say we have an object right here. That object is definitely moving. Let's say it's moving in that direction. It's in that positive z direction, I guess, is what we would call that. Or if you want to call this negative, that would be positive z. So it's actually moving in a positive z direction as far as its velocity goes. Its angular velocity would be pointed in our y direction. And maybe this whole thing's speeding up. If it's speeding up, then that means we have acceleration, some angular acceleration. So the angular acceleration would also be pointed, curl your fingers, in that upwards direction, while its tangential acceleration would still be pointed along the lines of that positive z-axis. And then you'd have some kind of centripetal acceleration, because, hey, it's moving in a circle, in the negative x-axis, because you got to point in towards the center of the circle. Alright? So we'll talk more about rotational motion. I'm going to make another video right after this, and we'll talk about how you can look at torques and balances of torques and all that stuff.